Welcome to Infoverse, the center for experiments, science, technology, and the investigation of all the strange and amazing things. I'm overjoyed to have you accompany me on this fascinating exploration and wonderment. This channel explores the fascinating realm of science, revealing the great wonders of nature and unlocking the secrets of the cosmos. We stop at nothing in our pursuit of knowledge and fascination, from perception-challenging experiments to mind-blowing technical developments that determine our future. High-speed trains and even some roller coasters use a magnetic braking system, set up in a way very similar to this, with powerful magnets, usually electromagnets, elevated above a conductive surface. The magnets slow the vehicle down quickly without any surface-to-surface friction that causes damage in conventional braking systems between brake pads and rotors. My favorite tabletop demonstration of magnetic braking is to swing a magnet toward a chunk of copper like a wrecking ball. The magnet loses all of its momentum at the very last moment in a way that almost looks supernatural. It reminds me of a scene in the second Matrix movie where Neo stops bullets in midair. The magnet's momentum is slowed by opposing magnetic fields generated by the flow of electrons in the copper. Since the electrical energy isn't being collected by a circuit for any useful purpose, it dissipates into the lump of copper as heat, so the copper actually gets warmer every time I swing the magnet toward it. By the way, you have such a smart idea. Magnets drop rather fast during free fall, but when dropped through a copper tube, they basically fall in slow motion while messing around. I realized I could finally answer one of life's biggest questions. What's the optimal number of these size magnets to get the slowest fall through this too? You see, dropping a single magnet results in a time of 1.73 seconds, and dropping 2 magnets increases this time to 2.86. However, dropping 45 magnets was even faster than dropping a single one, so I proceeded to do hours of back-breaking work to finally get the necessary data. And here's what it looked like. It turns out the optimal was 5 stacked magnets, and it took 5.71 seconds to fall. Something intriguing occurs when a magnet is dragged through the center of copper, an electrically conducting metal. The magnet's magnetic field is broken through by the metal, which then creates a magnetic field of its own, albeit in the opposite direction. Electromagnetic induction is the term for this phenomenon. This motion also produces an electrical current in addition to a magnetic field. The power of the magnet and the rate at which it moves through the conductive metal determine how strong the current is. More specifically, it depends on how quickly the metal penetrates the magnetic field. This idea serves as the foundation for both the magnetic motor and the notion of producing electricity using both kinetic and magnetic energy. A continuous flow of electricity can be created by continually moving the magnet close to the conducting metal. Electric motors and generators are just 2 examples of the many applications that make use of this theory. This phenomena is intended to be used by the magnetic motor to build a self-sustaining system in which the electricity produced drives the motor, which in turn maintains the magnet moving and sustains the production of energy. The idea of a perpetual motion machine, in which energy is generated from nothing, contravenes the principles of thermodynamics. It is vital to remember. The efficiency of converting kinetic and magnetic energy into electrical energy, as well as the practical difficulties involved, need to be carefully examined when building devices based on this notion, even though electromagnetic induction is a key principle in the generation of electricity. A remarkable illustration of electromagnetic induction and the interaction of magnetic fields with conductive materials is the interplay between a magnet and a copper tube. An amazing occurrence happens when a magnet is passed through a copper tube. The magnet moves through the tube at a substantially slower speed than it does when it moves through the air. The laws of electromagnetic induction and Lenz's law provide an explanation for this phenomena. A shifting magnetic field is created close to the copper tube as the magnet is moved through it. Lenz's law states that this shifting magnetic field causes an opposing electric current to flow inside the copper tube, and that this opposing electric current then generates its own magnetic field. This induced magnetic field works against the magnet's motion to prevent it from moving. The magnet moves more slowly through the copper tube because of the resistance provided by the induced magnetic field. Because there is more conductive material present in thicker copper tubes for the magnetic field to interact with, this resistance is more noticeable when the copper tube is thicker. As a result, the magnet must travel through the thicker copper tube for a longer period of time. In other words, the induced magnetic field's strength and size are influenced by the copper tube's thickness, which in turn affects the resistance the magnet encounters. The resistance rises with a thicker tube, which results in more resistance the magnet must overcome as it moves more slowly. This phenomena can be seen in a variety of experiments and demonstrations that use magnets and conductive materials. It illustrates how electromagnetic induction works by emphasizing the complex interaction between magnetic fields and electric currents. We may conduct fascinating experiments while learning more about fundamental scientific concepts by investigating these interactions between magnets and conductive materials. It is evidence of how intricately intertwined and complex the physical world is that we live in. Certainly, let's examine the interaction between a magnet and a copper tube in more detail, concentrating on the variables that affect the movement of the magnet and the behavior of the induced currents. The magnetic field of a moving magnet interacts with the copper's conductive qualities when it passes through a copper tube. The creation of an opposing magnetic field and the induction of electric currents are the two main outcomes of this interaction.